Good morning, class. Good afternoon, class. This is exam 2 review, chapter 3, differentiation rules, which we'll cover from section 3.1 to 3.8. For this part, we are going to cover sections 3.1 to 3.3. 3.1, derivatives of polynomial and exponential functions. 3.2, the product and quotient rules. 3.3, derivatives of trig functions. So the chapter covers those three sections, as well as the chain rule, the implicit differentiation, the derivatives of log functions, rates of change in the natural and social sciences, exponential growth and decay. And the couple of sections left are covered in the next exam: 3.9 related rates, 3.10 linear approximation and differentials, and hyperbolic functions. So let me give you the synopsis of what's coming up. Number one, the differentiation formula dy dx, that's the Leibniz's notation, is the limit of delta y over delta x as delta x approaches 0. And by definition, f prime of x is limit of f of x plus h minus f of x over h as h approaches 0. It's important to know, prior to the sections we're going to cover, we had to use definitions. Now, you can go to the PowerPoints, you see the proofs for this. So the derivative of x is 1. The derivative of c times f of x, where c is a constant, c can come out. The derivative of a sum is sum of the derivatives. The derivative of the difference is the difference of the derivatives. We use these two for limits, and then we use those to prove some of the formulas involving trigonometric functions. So the limit of sine theta over theta as theta approaches 0 is 1, whereas the limit of cosine theta minus 1 over theta as theta approaches 0 is 0. By the way, both cases, when you plug in, you end up with 0 over 0. So further investigation will give you those answers. Definition of a is such that the limit of 1 plus 1 over n to the power of n as n approaches infinity, that represents e. Or e is such a number that the limit of e to the power of h minus 1 over h as h approaches 0 is equal to 1. Those are some definitions. Now, we are going to use mainly these formulas for now. There are other formulas coming up. I will mention them. But for now, this is a constant. The derivative of any constant is 0. The dx of x to the power of n is n x to the power of n minus 1. The derivative of what's known as the power rule. Okay. The exponent sits in front and the exponent goes down by 1. The derivative of k times x, where k is a constant, is simply k. The derivative of sine is cosine. The derivative of cosine is negative sine, and you can look at the proof if you want in your basic PowerPoints. The derivative of tangent is secant squared. Cotangent is minus cosecant squared x. Secant x is secant x tan x, and cosecant, the derivative of that is negative cosecant x cotangent x. This is what we are going to look at for now. But there are other formulas. For example, this one is actually the same as this one. When you want to differentiate c times f, where f is the function, then you can take the c out. These two refer to these two. The derivative of the sum is the sum of the derivative, the derivative of the difference of the derivatives. Now, this is called the product rule. Fg prime, or f of x times g of x, if we differentiate it, is f prime g plus g prime f. I like this order because for the quotient rule, I can use the same thing with the negative over g squared. So f over g prime is f prime g minus g prime f over g squared. These are formulas that you need to memorize to be able to do the product and quotient rules. There are more formulas coming up. I'm not going to spend too much time on it for this time, but later on we need them. For example, this is the extended power rule, exponential rule, and so on. This is the composite function giving rise to the chain rule. Again, I wouldn't worry about it right now. And of course, logs. For example, the derivative of ln x is 1 over x, and the inverse trigonometric functions. We're not going to worry about that right now. As we come across them in other parts of this, I'll go over them again. So for now, let's stick with easy formulas, everybody. Let's stick with easy formulas, starting with the following. Y equals x to the power of 1000. And I want you to pay attention to this formula. The power rule, everybody. So according to this rule, 1000 sits in front, and then this goes down to 1000 minus 1. So the answer is 1000 x to the power of 999 using the power rule. Let me write the name. This is extremely important. So we come across this often. Okay, power. Okay, y equals 3r squared. Now, I can write y prime or dy dr. Is the derivative of this one. So never mind the 3r squared gives you 2r times 3 is 6r. I want to make sure we understand what happens. You can think about this as the part that you're concerned with, 3 times, and then 2 becomes the coefficient r to the power of n minus 1. This is 6r. Now, why am I writing it in this format also? This is in Leibniz's notation. See, when you write dy dr, you're telling your reader what is the independent variable. Remember, y in this case is a function of r, and it doesn't have to be. Okay, so we use the power rule on r squared. The 3 is a multiplier, it remains. All right, how about this one? Let's give everybody a moment. See if we can figure out the answer for this function. F of x is x to the power of 8 plus 12x to the power of 5 minus 4x to the power of 4 plus 10x cubed minus 6x plus 5. So we're going to write f prime of x equals, and we are going to look at each term. So let's do it term by term. X to the power of 8. What's the derivative of this? According to the power rule, anybody?
8x to the 7th.
Beautiful. What about this one?
60x to the 4th.
Beautiful, because this part will give you 5x to the power of 4, and you multiply it by 12. Minus 4x to the power of 4.
Negative 16x to the power of 3.
Beautiful, because it's negative 4 times 4x cubed. 10x cubed.
30x to the power of 2.
Perfect, because this is 3x squared times 10. How about minus 6x?
6x.
Look at this one, minus 6x. Simply minus 6 because the exponent is 1, everybody. When we don't write the exponent is 1. 1 minus 1, x
0.
is 1. So minus 6. And any constant, 5, 5,000, negative 2, 0. So this is the final answer, everybody. We're going to move on. And to differentiate this, we are going to use our algebraic techniques and distribute first. Before we do that, we are going to change this so that power rule can be used. So we're going to change the square root of x to the power 1/2. That's the first. The product of these two, remember the exponent for this one, which is missing, is 1. 1 and 1/2 becomes 3/2, 5x minus 2. So this is your algebraic step. Power rule. So when you want to multiply exponentials, this is the rule you use. And now, never mind that 3/2 is a rational number or any type of number. You just follow this. So x to the power of 3/2, 3/2 becomes a coefficient, and this goes down by 1. So it becomes 3/2, x to the power 1/2, plus 5, and any constant gives you 0. Now, again, I want to make sure we understand how we arrive at it. Three halves minus 1 gives you 1/2. And if we want to go back with the same format, then we're going to write it as 3/2 square root of x. Okay, everybody? Now, to do this, first we're going to do algebraic step. What would you do first here? What should we do first so we can use the power rule in essence? Anybody? A to the power of m over a to the power of n is a to the power of m minus n. So it's 2 over 9 x to the power of 5 minus 9 or negative 4. In order to use the power rule. And now we are ready to take the derivative, and that makes it f prime of x equals 2 over 9 times negative 4 x to the power of negative 4 minus 1. And I hope you see that this is minus 8 over 9 x to the power minus 5. And I hope nobody has any problem with algebra and exponential rules. So I remind you that a to the power of minus m is 1 over a to the power of m. So your algebraic techniques is the key. So going from here to here, it's just elementary algebra. Look, algebra, algebra, algebra. This is the only calculus. Can anybody tell me what is the answer to this one? d dx of pi squared. Anybody? The answer is 0. Why is that? because pi squared or E or 10,000 or 2 billion, those are all numbers, or 1/3, makes no difference. Any number results in 0. Its derivative is 0. Pi squared is a number, is 3.14159 to the second power. All right, we're going to use the product rule, and I want to do the very first step and do not simplify. Here's the reason. We really want to understand the concept. When we have f times g, we are going to differentiate one of them, multiply that times the other one, and add it to the derivative of the other one times the first one. So if I give it a name f, or f of x, the one in red, the one in blue, if I give it the name g, or g of x, according to this formula, I need f prime first, which is 4x cubed minus 6x squared. This is a constant, so it doesn't give us anything. It gives us a 0. So that's f prime. According to this formula times g. Just write the g. Plus g prime. Here's g. G prime is 3 times 2x, or 6x, minus 5 times f. Just write the red function now. Okay. Now, what I want to make a point of, why is it that I want to stop here? We shouldn't stop here. I want you to know that. I'm stopping here because this is the only calculus step, everybody. Of course, you have to distribute this one and this one, simplify, come up with the answer. But the purpose of this is just to make sure we understand the very first step, because this is the only calculus step. Needless to say, there are a few steps left in order to finish this, none of which are calculus step, okay? All right, to do this one, I'm going to put a raised dot here. So I want to make sure everybody understands I'm using the product rule. It's the product of f x squared and g sine x. So according to this formula, f prime g, I need f prime, which is 2x, times sine x, right? And then g prime f, I need the derivative of sine, which is cosine, times x squared. So I'm looking at combination of the product rule and trigonometric functions and power rules, you name it. So one more time, x squared gives you 2x. So let me just write underneath what we have here. We have f prime g as g prime f. And we're practically done. We just put the x squared in front. You can take the common factor of x out. There is no need for that. I want to do the same thing. I want to do a warm-up example using a quotient rule, meaning simplification is not of interest to me. I just want to make sure we understand how this works. So f prime g minus g prime f over g squared. So first and foremost, we're going to call the top the f function, x to the power of 4 minus 2x cubed minus 7. That is the f function. And 3x squared minus 5x is the g function. So given this y, we want to differentiate using the quotient rule. So first and foremost, f prime. So what is the derivative here? 4x cubed minus 6x squared, and this guy is 0. Okay. Then I need the g. Just put the blue one times 3x squared minus 5x minus g prime f. Here's the g function. The derivative is 6x minus 5 times the f function, the red function, just put it next to it. And then over g squared, the blue function, the bottom, put it in a parenthesis and square. And we're done. Again, for the warm-up example, needless to say, now you continue with your algebraic steps to simplify the numerator and move on, but that's not the purpose of this question. So we had to use the quotient rule, and whenever we have to use either one, we shouldn't avoid that. However, are we using the quotient rule here, or better yet, do we need to use a quotient rule? And of course you can use it, but you don't have to, because all you have to do, make up two fractions. This is 1, gives you 10. This is another one, gives you minus 7x. So here's the two fractions. Here's one of it, one fraction. Again, this is elementary algebra. Here's the second one. And as you can see, the answer is minus 7. So you don't have to do much. You don't need to do the quotient rule. This is a constant 0. This is minus 7 when you differentiate. We want to find the following limits, and before we do that, let's remind everybody of the limit of sine theta over theta as theta approaches 0 is 1. The limit of cosine theta minus 1 over theta as theta approaches 0 equals 0. We can use these two that we have already established to prove others. We notice that this is the product of sine 3x and sine 5x. So we can make this into two fractions, sine 3x over x, sine 5x over x. Now we look at this one and we notice that if the argument of sine, and by the way, you can never ever change the argument of sine, is equal to the denominator, you get 1. So this argument is intact, you can't change it. If this was 3x, then we could do something. Well, not a big deal. I'm going to multiply this by 3 over 3. This one, I need 5x. Not a big deal. I'm going to multiply by 5 over 5. So I'm going to multiply the first one by 3 over 3. This is 1. And the second one by 5 over 5. And now I'm going to use the limit laws and separate the first from the second one. And I'm going to bring this number 3 out, this number 5 out as follows. So take a look. This number 3 came out. This number 5 came out. This one remained. This one remained. Now, if you just change it right now, this one to 1 and this one to 1, the product is 3 times 5 is okay. But honestly, you want to pay attention here. This one and this one and this one must be the same. For this one, I'll show you. Because x is approaching 0, so is 3x. So this must be changed as follows. This must be changed to the limit of sine of 3x over 3x as 3x approaches 0. Because when x approaches 0, so does 3x. What about this part? This we should change to the limit of sine 5x over 5x as 5x approaches 0, and this is also 1. So 3 times 1, 5 times 1 is 15. This is how you justify it. Okay, everybody? All right, how about this one? Well, when we look at this one, if the denominator was theta, would be 0, but it's not. So what do? We divide the top and the bottom by theta. Now we make up two limits, the limit of the top and limit of the bottom. The top is 0 according to this. The bottom is 1 according to this. 0 over 1 is 0. So that's how we justify the answer. So these are the limits. The limit of cosecant x times sine of sine x as x approaches 0. That's what we want to figure out. When we look at this, when this one, and this one are identical, that's how we arrive at 1. Well, we know cosecant is 1 over sine. This can be replaced with 1 over sine x. Now, these two are the same. But this is not the same as those. As you know, when x goes to 0, so does sine x. So now, if I let sine x, let this one be theta, and this one, sine x, is also theta. Now this is equal to 1. Again, I want to make sure everybody understands that three things must be identical. This one, the argument of sine, the denominator, and this one, if they are not the same, you have to make them the same. Is x the same as sine? Absolutely not. But when x goes to 0, you know sine x is 0. Sine of 0 is 0, right? So when x goes to 0, sine x goes to 0. What about this case? Again, we want to make it look like what we know. This is x squared. This is the argument of sine. You can't change that. So if you can't change that, maybe we can make this one look like that. So we're going to multiply by x, the top and the bottom. When we do that, now the denominator is x squared. And this one, we can say the limit of x. So we can write it in this fashion. So we keep this part separate. So it's the limit of the x times sine x squared over x squared as x approaches 0. Now notice, when x approaches 0, so does x squared. So for this one, the argument of sine, the denominator, and this must be identical, and they are. Again, when x goes to 0, so does x squared. And of course, this is 0, this is 1, their product is 0. We have the derivatives here of trigonometric functions. The derivative of sine is cosine, cosine is minus sine x, and we use limits and trigonometry to prove those. The rest of them we really don't need to, because we know the reciprocal identities and quotient identities in trigonometry, so we can use that. We know tan x is sine x over cosine x. We want to prove that. So I'm going to remind you, tan x is sine over cosine, or 1 over cotangent x. Cotangent is cosine over sine over 1 over tan x. Secant is 1 over cosine. Cosecant is 1 over sine. Sine squared plus cosine squared equals 1. So any of them you want to prove, any of those, you just use the quotient rule. For tangent, you put sine over cosine, do the math. For cotangent, after you prove that, you can go with either 1 over tangent or cosine over sine. For secant, change it to 1 over cosine and prove it. For cosecant, 1 over sine and prove it. So you use the quotient rule. How are we going to use that? Just pay attention to this. We are going to call this the f function, and the denominator is the g function. So I need f prime g minus g prime f over g squared. So f prime, the derivative of sine is cosine times g, which is cosine, minus g prime, the derivative of cosine is negative sine times f, which is sine, over g squared, the bottom squared, cosine squared. So I hope you see what we have here. Let me write. So this is f prime, this is g, minus, this is g prime, this is f, this is g squared. The top is cosine squared plus sine squared. As you know, cosine squared and sine squared is the same as sine squared, plus cosine squared, the numerator is 1. And 1 over cosine is secant, so 1 over cosine squared is secant squared x, and that's a proof that the derivative of a tangent is secant squared. We just proved that. I highly recommend you try at least 2 of these using the quotient rules. So I'm going to do one more, maybe y equals secant x. And I'm going to write it as 1 over cosine. And I'm going to use the quotient rule on that, where this is f, this is g. The f function is number 1. The g function is cosine x. So I need f prime g. The derivative of any number is 0 times cosine x, minus g prime f. The derivative of cosine, negative sine x times 1. And just write the bottom and square it. As you can see, this is 0. This is negative, negative, plus sine x over cosine squared. Now, remember, the derivative of secant is secant times tan. So we want to make it look like that. We're going to write it as 1 over cosine times sine over cosine. The reason we do that, because we know this is secant, 1 over cosine is secant, and sine over cosine is tangent, and we are done. We just proved the derivative of y equals secant x is secant x tan x. So we proved that. Trigonometric identities, many of them you need to be comfortable with. These are some of them that I wrote for you. This is part of what we call Pythagorean identities. There are 2 more. I'll discuss it with you in a moment. We want to differentiate this. Obviously, we are going to use the quotient rule by calling this the f function and this one the g function. So y equals 1 plus sine x over x plus cosine x. 1 plus sine x is the f function, x plus cosine x is the g function. And now we want y prime. And so we start with f prime. The derivative of the top is cosine times g. Just put this in the parentheses here. Then we want g prime. So the derivative of the bottom is 1 minus sine x, because the derivative of cosine is negative sine. So 1 minus sine x. And you put f just the way it is in the second parenthesis. Now you write the bottom in a parenthesis and square it. And we're done with calculus. We're just going to finish using our algebraic techniques as well as trigonometric techniques and knowledge of trigonometry and its identities. So this is x times cosine x. This is cosine squared. The product of these two, we should know it's 1 minus sine squared. We keep the negative out. Everybody remembers a minus b and a plus b. The product is a squared minus b squared. Now, since sine squared plus cosine squared is 1, we should know that 1 minus sine squared is cosine squared, for example. So the Pythagorean identities that I mentioned, one of them last time, sine squared plus cosine squared is 1, tan squared plus 1 is secant squared, 1 plus cotangent squared equals cosecant squared. You should know all of them. And if you know this one, then you should know if you move the sine squared, this becomes cosine squared, okay? So this is cosine squared with a negative sign in front of it. These two cancel each other. And we are done. Trigonometric identity is extremely important. We're going to move on with differentiation of y equals 1 minus secant x over tan x. And again, the top function, 1 minus secant x, I'm going to call it the f function. The bottom function, tan x, is g function. And we are going to use the quotient rule. F over g prime is f prime g minus g prime f over g squared. And again, I'm going to mention in that class, the reason I put it in this format, because if you have already seen this, they have a slightly different format. To me, it's easier to memorize it in this manner. So, sticking with this, f prime g. So I need the derivative of the top. This is a number, whatever it is 0, minus secant is secant x tan x. Take a look. The derivative of secant x is secant x tan x. You can use it for now, but you have to memorize it, class. So you're getting started. It's okay for the starting. So we start with that. So minus secant x tan x and times g, just times the bottom, tan x. Minus g prime, the derivative of tangent is secant squared. The derivative of tangent is secant squared. So minus secant squared times f, the top function, just write it here. 1 minus secant x over the g squared. Just repeat that. Write it here and square it. Tan squared. Tan x becomes tan squared here. And we're done with calculus. Again, let me in fact put an asterisk next to it. I want to really emphasize this, class. We are done with calculus here. And that is my point. If your knowledge, prior knowledge of mathematics is good, calculus becomes a piece of cake, because you normally have one step of calculus. Everything else is algebra, geometry, trigonometry, you name it. So let's simplify. First, this one is minus secant x tan squared minus secant squared x plus secant cubed x. To simplify, we notice there is a common factor of secant in there, so we can take out a secant x. If I take a secant x out from the numerator, I get minus tan squared minus secant x plus secant squared x. All I'm doing is algebraic technique of factoring. Now, if you recall, one of the Pythagorean identities in trigonometry is 1 plus tan squared is secant squared. So if I move the tan squared to the right, I can say secant squared minus tan squared is 1. And therefore, this one and this one, isn't that the right side? Look at this one and look at this one. These two are right here. That would be 1. So replace the sum of these two with number 1, and we are done. This is as simple as it gets. There are other ways that you can simplify it further. We're not going to go with that. Sometimes in trigonometry, to simplify, you represent everything as a function of sine and cosine. Or in fact, if you want to simplify and you don't know how to do that, you use sine and cosine to do the simplification. I'm going to differentiate this, and again, I'm going to call the numerator f of x, the denominator g of x, and we are differentiating y equals cosine x over 1 minus sine x using the quotient. So f over g prime is f prime g minus g prime f over g squared. We start with f prime. So here's f prime, the derivative of cosine minus sine x times g, just times the denominator, 1 minus sine x, minus g prime. Okay, now we want to take the derivative of the bottom. This is a number. It doesn't matter what number. The answer is 0. Negative sine x. The derivative is negative cosine x. So this negative sign remains. Minus sine x gives you minus cosine x times the top f times cosine x. So this is it. Over the g, which is 1 minus sine x squared. Now let me write this. I want to make sure we understand that we have f prime g minus g prime f over g squared. And again, we're done with calculus. We are going to simplify. So let's distribute minus sine x. Let's distribute minus and minus plus sine squared. Let's distribute minus minus plus cosine squared. We notice if we put these two together, we get 1. So what do we have? We have 1 minus sine x. In the denominator, we have the same thing to the power of 2. So the numerator is 1 minus sine x. The denominator is 1 minus sine x squared. One of them goes away from the bottom. The top becomes 1. That is the simplification. So this is minus sine x plus 1 cancels the exponent, if you will. And that's your final answer, everybody. Y prime is 1 over 1 minus sine x. You want to find an equation of a tangent line to the graph of the function y equals e to the power of x times cosine x at the pair x comma y 0 comma 1. And To do that, remember, to find the equation of a tangent line, you need two things. You need a pair, x comma y, it's given. By the way, again, they may just give you the x coordinate. If you plug in e to the power of 0 is 1, cosine of 0 is 1, their product is 1. So even the x coordinate will result in what you want. The second thing is to find the slope. To find the slope, let's differentiate the function. And we notice it's the product of e to the power of x and cosine x. So I'm going to put a raised dot here. And therefore, I'm going to use the product rule. All right, e to the power of x, remember the derivative of e to the power of x is itself. So e to the power of x. So we are looking at f prime g. Let me write f and g. So we have f times g. So we want f prime, which is e to the power of x, times g cosine x, plus g prime. Now, the derivative of cosine is negative sine. So plus negative sine times e to the power of x. So in one shot, I write minus. So let me write it for you. So f prime g plus g prime ft. G prime itself has a negative sign because the derivative of cosine is negative sine, okay? The derivative of cosine is negative sine, that's why. So we do have a plus sign, but this creates a negative sign. And so let's factor out e to the power of x. It looks better that way. We want to find the slope. So replace the x with 0. And we get 1. Let me just quickly show you why it's 1. Because e to the power of 0 times cosine 0 minus sine 0 equals, this is 1. Cosine of 0 is 1 minus 0. And the answer is 1. Now, instead of using y minus y1 equals m times x minus x of 1, I'm going to use y equals mx plus b because this telling us that b is given, everybody. This is your y-intercept. So y-intercept is given. I don't have to go through point slope. Y equals m 1 times x plus b. It so happened that m and b are both 1. Don't mix them up. This one was calculated as 1. This was given as 1. So finding an equation of a tangent line, this time we use the easy way out formulas instead of the definition. All right, we want to find the points for which the tangent lines are horizontal. Now, what that means is we are interested in lines that are tangent lines, and this means their slopes must be 0 because horizontal lines they have slopes that are 0. So what do? Well, we take the derivative of the function f prime of x first. 3x squared minus 6x plus 0. We don't write this here. So 3x squared minus 6x. And since horizontal lines, they have 0 slope, and remember, f prime of x represents infinitely many different slopes of tangent lines. You set this equal to 0 to find the points. If they said, for example, find the points for which the tangent lines have a slope of 7, then you would set this equal to 7. Have a slope of -2, you set this equal to -2. That's exactly the same concept. When they say it's horizontal, they don't have to give you the slope. You should know the slope is 0. So we factor out the 3x. This says x is 0, this is x equals 2. By the way, I hope you remember 3x or 3000x or minus 3x makes no difference. The fact is x is 0. And then this says x is 2. Now, they may be good enough with the answer x equals 0, x equals 2. But most of the time, they may be interested in pairs. And not only that, I don't want anybody to be under the assumption that means the pair 0, 2. That's not the meaning of it. So plug in 0 into the original function and clearly gives you 5. So the first one is easy. If you plug in 0, you get 5. So one pair has coordinates 0, 5. Now let's plug in 2. So if I plug in 2 here, I get 2 cubed minus 3 times 2 squared plus 5. 2 cubed is 8. 2 squared is 4 minus 3 times 4 is minus 12 plus 5. And they add up to 1. Therefore, the second number x equals 2 results in the pair 2, 1. 2, 1. And that's the second pair. There are 2 points having tangent lines that are horizontal.